All right, and welcome back to a Randall Carlson podcast, Cosmographia. Here again, Randall Carlson, and we got with us tonight our good friend Chuck Kizina. Been on multiple tours with us, is a planetary scientist with specialization in geology. Had a lot of involvement with environmental regulation, and he's going to give us all kinds of feedback and perspective on some of Randall's recent articles in the newsletter. If you're not getting the newsletter, sign up for those. And Randall, we got a lot of different directions we could go, a lot of things in the news, lots of new papers about megafloods, about
Yes,
asteroids whizzing by,
all
tours
of the
coming up.
things.
Yeah, so multiple directions. And welcome, Chuck. Good to have you, buddy.
Yeah, thanks. Great to be here.
Yeah, I'm glad you introduced him because I was kind of wondering now who is that distinguished looking character that is sitting at the bottom of my monitor screen. And now I recognize him. Yes.
Yeah.
So you have been, well, the thing I was thinking about you this past weekend as I was trying to navigate through a couple of the world's biggest airports was I wish I had Chuck here with me to help me with all of this.
Yeah.
But I figured it out.
I fly a lot. I do travel a lot, as you know, and it's yeah, I wish I was there with you too, but it's always fun when we travel together. That's
It is. Well, we're going to do that again, aren't we?
Oh yeah, for sure.
Well, you
Well,
know
do we have
what?
anything?
Chuck helped me get to Egypt. I don't know if I would have gone to Egypt the first time a year and a half ago if he hadn't said, "Hey, let's split a room. I help you get a deal on a plane ride." And I was like, that sounds pretty
Yeah,
good.
it worked out. It was a lot of
Yeah.
fun.
Yeah, we
Yeah.
went to Egypt together with the big tour.
So
I
you
gotta
will
think-
not be doing the Columbia Gorge tour.
I can't.
Yeah, that's what I heard.
Yeah. No, I'm
yeah.
booked up.
And I know you'd rather be doing that than what you are going to be doing.
That is true. I'd rather be with you guys. I'm in a spot right now. I've got some things to wrap up, and when you
Mhm.
say you're going to do something, you do it. So,
That's right.
but there'll be future trips.
Oh, yeah.
Policy.
Yeah.
So I thought it'd be kind of fun. Every month I put out a newsletter and I try to cover things that are in the news that would be interest to those kinds of subject matter and topics that we're interested in, geological, astronomical, and ancient history and how it might all tie together and so on. And every month, I'm going through scouring the literature, which I do anyway. So I figured, well, I might as well do a newsletter and report on some of the stuff that I read on. I mean, I read between 20 and 30, or I'll say I'll peruse between 20 and 30 scientific journals every month. And so when I see stuff that catches my attention, I like to flag it, and then that goes into the newsletter. But I always see more stuff that's going on out there in the world of science and geology and ancient architecture and astronomy and all that than I could possibly report on, right? So there's a lot of extraneous stuff, I guess you could say, that I've accumulated that didn't make it into the newsletter. So I thought it might be fun to look at some stuff maybe that's been in the news, this year, maybe the last 6 months or since spring, that might be of interest because there's actually quite a bit of stuff. And I don't have, I don't have it all categorized and organized according to a specific plan of attack, but I do have enough things right at my fingertips that I could pull up some stuff. And I think we'll start with a report that came out in March, I believe it was. Let's see. Which was one that didn't make it into the newsletter. Yeah, March 9th, 2024. It was, where was this journal? Let's see, I'll figure it out here. Let's see. Oh, this was just Science News reporting on it. And I usually will start at Science News and then Nature and Science, those three journals, which are kind of the mainstream. Science News, of course, is totally for popular consumption. But what you do is you read the report in Science News, and then you follow the reference to the original work and where it was published. Anyways, we don't need to do all that, but this is what it was. This is the title of the article: Rocks Betray the Oldest Known Airburst.
Yeah.
An asteroid exploded over Antarctica. not surprising, 2.5 million years ago. So the timing estimated from the age of the ice makes the mid-air detonation the oldest known airburst. Scientists report in the February 1st Earth and Planetary Science letters. Airbursts come with shock waves and heat, but don't make craters, which is a point we've been emphasizing for years, is that you're not going to really know the full picture of impact events if you're only counting craters. For a long time, estimates of impact events have been based upon crater counting. Although I think that we're seeing that that's beginning to change now. Anyways, this was not if it did, would have been into the ice itself.
And the number is about 200 right now across the globe.
I think it's
identified, right?
Yeah. And that's roughly over 15, maximum 20% of the actual surface of the Earth. Now, for purposes of just a framework of thinking, I would assume that the distribution of craters around the planet, at least I would start with, this would be my working assumption, is that craters around the planet are going to be relatively homogeneous and uniformly distributed if we had all the points of impact located. Just like if we look at the moon, you'll see that there is pretty much almost total saturation of the crust with craters, right? Now, the moon, obviously, unlike the Earth, it preserves craters. Earth eats craters. So if there's 200 craters, let's say, and that's roughly 15% of the Earth's surface, because what is the ocean? About 70%, right?
Yeah.
72%. So if we had 15% of the Earth's surface, that means 85%. Now that could include the oceans, Antarctic ice sheet, Greenland ice sheet, uninhabited areas of the world, of the planet, astroblemes, which aren't necessarily craters. Chicxulub in the Yucatan Peninsula is an astrobleme, but you don't really, it's not an obvious crater like, the crater at Winslow, Arizona. Which one I'm talking about, Chuck?
I do exactly know.
Yeah, because you've been down there.
I have. It's pretty obvious that just looking at that one.
Yeah.
But yeah, they're all not the same. And as we learn how to look and how to see, our techniques are better, right? To spot them. We find more and more.
We find more and more. And the more we get the ability to peer under the surface, we're seeing things. But so the point I guess I'm trying to make is if, Brad's number, we're getting very close. I think in round numbers, it's probably safe to just use that number of 200. Well, so then we have to go 100 divide by, say, 15. Or if we want to be conservative, we'll say that 20% of the Earth's surface has been surveyed to the extent that we would see. So we could multiply that by 5 and we'd get 1,000 to 1,200 impacts that could have left craters or, into the ocean, which of course would have then created tsunamis, or into areas that are now under ice sheets or that we don't see because they're under rainforest or whatever. I mean, because if you look at the craters, the distribution of craters, obviously, even on land, they're not uniformly distributed. Obviously, there's a direct connection between the density of population of an area and the fact of craters being discovered in it, right? And then, of course, also, you're going to see anywhere where you've got exposure of the land surface, like in desert areas, you're going to be more prone to finding them, where there's probably a lot more of them hiding under rainforests and boreal forests and all of this kind of stuff. So they're not as obvious.
When where I grew up, and we had in the neighbors' fields, there was an area there that the grass always grew a different color, and it was circular. And that was from an impact in the 1800s or so. It was small impact, but when I grew up, it was well known. It was reported in the area, and they did try to dig up whatever was impacted. And I was told that at the time they took it into General Electric to have a metallurgist look at it, but I'm not sure what they found or if they found, but guaranteed as the years went by, and even now, you could tell when I was a child, this isn't very long ago, right? I mean, for me, it depends, that's a matter of opinion, but in the last 60 years, it went from, or last 100 years, you could see it, and then it would change. It was not as much of a depression, not as much. Now there's trees on it.
Yeah.
Now if I didn't know where it was, there was no way on this earth anybody would
Right.
know that's where that impact was. And that was in such a short period of time, less than a lifetime.
Yeah.
Yeah.
So that
Like you said, it's been
right.
eaten or digested.
It's exactly,
Yeah.
The Earth has swallowed it up and it's invisible almost.
So let me finish this. There's a little bit more of interest
Sure.
here. So it says airbursts come with shock waves and heat, but don't make craters. So there's scant proof of the explosions in the geological record. The two other known ancient events date to about 450,000 years ago. I'm going to have to look up and see what those are. So cosmochemist Matthias van Ginneken of the University of Kent in England and his colleagues chemically analyzed 116 rocks, each about the width of a human hair, dominated by olivine and spinel materials that you were just talking about with Brad before we started. Would you like to go ahead and tell us a little bit more? What is a spinal material?
Spinels.
Spinel, thank you. Spinal material is what's in my backbone, right?
Yeah, exactly.
That achy thing.
That's that achy thing at the bottom of my back.
Must have been on your mind.
Spinel.
That must be spinel. Thank you.
Yeah.
I will now, for the rest of this incarnation of my life, know spinel.
And you'll see these minerals as gemstones. I mean, if you go to a store, you'll see olivine is peridot, known as peridot, and spinels are known as spinels, and they look like they're a variety of colors, but they look like, now not in the microscopic sense like they're looking at here, but a larger spinels will look like sapphire. For the most part, they're beautiful. But
so tell us, what is a spinel?
It's I can tell you how you can get there, and this is the interesting part of this, is that it's when you have a geology, or the creation of minerals is like baking a cake. You have something you start off with. It's a certain amount of ingredients, and then under different pressure, temperature conditions, you get different, right? You get different. Olivine will drop out of solution first, and then you'll get other things like spinels, a wide variety down to quartz. And what was going through my mind when I read this too, I thought, it's, how do you form? It takes a long time. It takes time to get a crystal and lattice up to get a crystal form. And if they're seeing spinels or seeing olivines, the first thing that came to mind is, where'd that come from? Because I don't know that there is heat and pressure in the airburst, but I'm not well versed enough to know that it can happen that fast. So did it come in with it, and it's just fragments of something that came in with the airburst? I went through it. I'm not quite sure that they do think it interacted and had some with the
Okay. So it says dominated by olivine and spinel minerals, the rock's chemical composition is consistent with an asteroid. And I have here the definition of the spinel is a hard, variously colored mineral with the composition magnesium, aluminum, and oxygen, having usually octahedral crystals. Okay, that's interesting to know. I really like octagons. Brad can confirm that. And occurring in igneous and metamorphic carbonate rocks. Okay. The red variety is valued as a gem and sometimes confused with a ruby. Also, it's any of a group of minerals that are oxides of magnesium, iron, zinc, manganese, or aluminum. So there we go. So it's an oxide of manganese and aluminum. So
yeah, you see what I mean?
That's what it is. So basically, then the spinel minerals and olivine, it says here, are associated with asteroids. What's more, the rocks appear to be multiple pieces fused together, indicating that they formed in a dense cloud of material. I should probably go to the original article in Earth and Planetary Science Letters for the details, because that's all it says. But so let's see. Oh, well, we could.
Was that some kind of a typical proxy then for identifying impact sites? Not well, like a crystal, not a platinum group metal, which we talk about lots of
I
the
think
other
it can
big ones.
vary. I think
Yeah, and this, I guess we have to now try to understand the difference, the geochemical differences between ground bursts and air bursts. Because we're looking at an air burst here. So you're not going to have, well, that's the question. I think that is a question that's been raised. Can you have shocked quartz in air bursts?
That I never thought about. I know that, if you have a palisite, you'll see olivine in it, right?
Uh-huh.
So it's not uncommon. So to answer Brad's question to a certain extent, if pallasites will carry this stuff with them.
Okay, so Brad, do I have screen sharing?
You sure should. Give it a try.
Okay, then I am going to share my screen too. And this is right from the article here. So you can see microscopic Antarctic rocks. 3 of them are shown. They came from an asteroid that exploded in the atmosphere millions of years ago. So look, this is what they're talking about, that there's smaller stuff fused. So that indicates a pretty high temperature. You're seeing this, aren't you, Chuck?
I am. I had to stop my watch from dinging.
Well,
I do. I see it.
mm-hmm.
Yeah, and you see the spherical nature of it. I mean, that's
Right here you see
that's
it.
definitely from something that melted and then re-solidified.
Yeah, here. I wonder what it doesn't. Probably in the original article explains what we're seeing here with this pattern.
Yeah,
I don't know what that
it
is.
looks like there's some mineralization, but I can't say for sure.
Well, geez, man. Well,
why am I here?
I thought we brought you on to explain everything to us.
If I could, I would.
So 50 microns, that's pretty small.
Yeah, it's really small.
Smaller than the width of a hair, they said.
It's astonishing they can even find them. Yeah.
Well, it is. But I imagine, it's in the layers of ice. That's the thing. That's how it got preserved. So by counting the layers back, they can estimate that that it was 2.5 million years ago, which is very close to 2.6 million years ago. And there we go, 1,000 precessional cycles. That's basically 1,000 precessional cycles ago. So in other words, that's very, very close to the Pliocene-Pleistocene boundary. That's what I'm getting at.
Right.
Very close to, which is dated at somewhat less than 2.6 million. However, if the case is that impacts are not randomly distributed in time, we were just talking about impacts being randomly distributed in space, right? But if we don't assume that impacts are randomly distributed in time, then the obvious assumption is that they're clustered in time. So I think a lot of the early criticisms of impact-induced mass extinctions and impact-induced geological boundaries, which have a high degree of correlation, were associated with impacts. But when you have a condition where the climate shifts that are manifesting the shift from one boundary, from one geological period to another, or you look at the extinctions, which the old oversimplified assumptions is, oh, well, it couldn't have been an impact because it would have been all at once. No, guys, no.
Yeah.
It doesn't work like that. All the evidence points to the fact that there may be bombardment episodes, and that the rate of bombardment is not uniformly distributed through time. So it's just, you could, in my picture of this, the model, let's say, of mass extinctions is a lot more complicated. And that doesn't rule out impacts as being involved. Because for one thing, we know that there's going to be feedback. We already know just from the Tunguska event that there were feedbacks that affected the climate for several years. There was a massive destruction of ozone from the Tunguska, which was just what, a 50-meter object that came
small.
in, right?
Yeah.
Right. So imagine what like a flurry of Tunguska like. Now, see, if Tunguska was associated with the comet Encke, which there's a high degree of probability that it was, or the progenitor of comet Encke. Encke is a prominent or cometary body within the Taurid meteor stream. And the Taurid meteor stream intersects the Earth's orbit in two zones. One, it crosses in the summer, late June, early July, which is the just after the perihelion passage of the stream coming from around the sun. It peaks right around the end of June, early July, right? That's exactly when the Tunguska event occurred. So the timing of the Tunguska event was consistent with it being a member of the Taurid stream, right? Early morning, that the time of day was consistent, the time of year was consistent, and the radiant point in space was very close to the Beta Taurids. So in other words, its entry into the atmosphere is pretty much where a Taurid meteor, which would have been. So you've got the radiant point in space, and you've got the timing. Does not prove that was, a member of the Taurid family and therefore related to comet Encke, but it creates a strong circumstantial case that that's what it was. Okay.
Yeah. And I'm of the belief, like you are, these asteroids, they're anything moving around. They're not riding alone. They're riding with friends.
Yeah, often they're riding with friends. We're seeing that now.
Yeah.
And in fact, when you look at the pattern of forest destruction, it's really more butterfly. It's not elliptical. Like if you had an object coming in, right, at an oblique angle to the surface, it detonates 5 miles up. That shock wave would create an elliptical blowdown. But it's actually butterfly shaped, almost as if you started with an ellipse, but you actually had two, right? So what that suggests to me, looking at the pattern of forest blowdown, is that there were two objects either going very close to each other or maybe splitting as they're entering into the atmosphere. I don't know which.
Breaking
apart. It looks that, like, by the time it got to the detonation level of the atmosphere, about 5 to 8 miles up, at that point it had separated and was two separate objects that sort of blew up independently. And that could be consistent with some of the eyewitness accounts, particularly the audio effects. A lot of people reported like 2 explosions, even 3 explosions. But my point was that it had enormous consequences for the ozone layer, right? So then you got to ask, well, now, of course, then what happens when you reduce the ozone layers? You increase galactic ray bombardment. That has a whole set of potential consequences and feedbacks. And if you had direct impacts, you're probably affecting the tectonic stability of the Earth's plates. We know that there's a correlation between impacts and large-scale volcanism. The formation of large igneous provinces appears to be very closely associated with several of the great impacts in Earth history. So we could be looking at a whole series of consequences just emanating from one impact or several impacts. But then if you spread out those impacts so that they're maybe separated by thousands or 10,000s of years, but part of this still, like early on in the infall of the original progenitor comet that would have spawned Encke and Oljato, the Beta Taurids, the Tunguska event, the 1975 bombardment to the moon that occurred in the end of June, all of those things, right? So when that came in, it was likely a really big comet nucleus. Now, I think that if it comes in, as most of the estimates are, that it would have been between 20 and 30,000 years ago that I've seen, which to me implies that it was probably somewhere in the middle of that, around 25 or 26,000 years ago. And one reason I think that is because there was a major climate shift right at about 26,000 years ago. And this was the shift into what has been called the late Wisconsin period of the Ice Age. And it involved a sudden drop of temperature and a sudden increase in the growth of ice sheets around the world. So, again, no proof, but it makes a plausible case that perhaps the original progenitor comet came in as it began to fragment. Earth would have encountered the byproducts of that hierarchical disintegration, and it could have, it could have a signal that lasted for several thousands of years. And to say that, well, and this is one of the things with the Younger Dryas boundary critics, why they're dismissing the Younger Dryas impact idea, is because of the fact that it does appear that the full mass extinction of the late Pleistocene megafauna may have taken about 3,000 years. Although the final curtain, for the most part, dropped right at 12,009. But it looks like there was bleed through. It looks like there was survival.
Yeah, there was. There clearly was.
Yeah. But after 11, I think then there was a final. So in other words, I think that the extinction probably took place in 3 phases.
I think the way that I look at it too, this is messy business. It's not imagine like in a painting, there might be just, then there are single impacts and whatnot, but anything that's large is not only going to have an impact, there's going to be a reaction at the antipode, right?
Yes.
And there's going to be that. And then, so there's that knock-on effect. And then the mess that got sprayed out into the neighborhood is going to accumulate and still keep raining down over time. And we're probably still seeing some of that. And it's just like you said, it's a variety of methods. There's no one clean answer, but it is messy business.
Yeah. There was a very
complex.
interesting, let's see, this came out.
Well, let me add something in there before you get
Yeah,
too far
please
afield
do.
there, Randall.
Please
I don't know if we'll have time to get back to it. But yeah, since you got into Torrids and Tunguska again, right? The June 30th date that comes around, and that's the anniversary of Tunguska 1908. So on the 29th, right, one just came by this year, 6 weeks ago, right?
Yep.
Within the distance of the moon, which is quarter
Yeah,
million
and
miles. Right?
And a big one at that.
You're getting around there, yeah, an 800
I
footer.
got something to pull up on that.
Okay, so just in case we didn't get back to that, I want to make sure that
Well,
people
good.
are paying attention to the news. If they're not, these kind of things are happening, and you can watch specifically annually on those dates. And be seeing things because that stream is not cleared out. There's still a lot of debris in there, and some of it's pretty sizable. Obviously, 800 feet width could create quite a level of destruction we don't want to deal with here.
No.
So and I'll pull that. Excuse me, I'll pull that up here in a second. Let's see.
Okay, well, good. Yeah, I didn't know if you had that ready, but I didn't want to pass that up since it did just happen.
Yeah, not only, now get this, here we go. June 27th and the 29th of this year, NASA's planetary, now this was on the Jet Propulsion Laboratory website, NASA's planetary radar tracks 2 large asteroid close approaches. Okay, so it was asteroid 2011 UL-21 and asteroid 2024 MK. So let's see.
2024, meaning they just found it.
Yeah. Yep.
But you're going to get there.
So when you see asteroids, the naming of asteroids, they always give the year of the discovery first. So asteroid 2011 UL-21 obviously was discovered in 2011. And then oftentimes the discoverers, it'll be their initials, that'll be attached to the name. Now, let's see. The asteroid 2011 UL-21, it was a pretty long ways away. It was over 4 million miles. But it was 1 mile in diameter. And like you mentioned earlier, this one particularly had also had its own little moonlet,
Yeah. They're
orbiting
buddies.
1.9 miles from the surface. Now, 1 mile, okay, I mean, even if that's huge. Now, if that had hit the Earth, that would be a global catastrophe. Now, it probably would not cause global mass extinctions, but it would certainly cause regional mass extinctions. And it would probably spell the end of civilization as we know it. It would not cause the extinction of the human species. People would survive that. But it would probably cause the extinction of civilization. And the people who did survive it would be pretty much living back in the Stone Age. That's almost a certainty. Unless, of course, we were prepared for it, which we are not now, but we could be. And that's something we maybe should talk about. But
we will.
Just for fun, I did the calculation based upon volume compared to Tunguska, which was a low density object about 50 meters in radius, or about 150 feet, 160 feet in diameter. Okay. So just using a simple formula for the volume of a sphere, and of course these objects tend towards sphericality, but they're not spherical. But what it can do is get us into ballpark. Okay, so this thing at 1 mile in diameter, let's suppose it's roughly spherical, would be about 43,000 times larger than the Tunguska object. 43,000. Now, obviously, that could be 40,000, 45,000. It's going to be somewhere in that ballpark, though.
By mass?
But no, by volume.
By volume. Okay.
Now, an asteroid is going to be much denser than a piece of a comet. The Tunguska object appears to have been a low-density object, which makes it far more likely that it was a piece of a comet, which again feeds into the idea that it could have been part of the torrid stream, which ultimately emanated from some large unnamed comet, of which Encke is now the remnant of the original really big comet that came in. So just over 4 million miles, that's, 16 times the distance of the moon. So, no big deal, right? But I don't think that's the takeaway here. And we'll come back to that in a second. Let's jump over to asteroid 2024 MK. It was discovered on June 16th. Okay. So it was what? It came in on June 29th. So we had a 13 days of lead time. Okay. 13 days. So discovered June 16th, flew within the orbit of the moon on June 29th. Okay. Its diameter approximately 500 feet. Now, that works out to be about 37 to 38 times greater by volume than the Tunguska object. Now, we know that the power of the impact is going to be a function of a couple of things. One, the two things primarily, tell me if I'm missing anything here, Chuck. It's going to be velocity and density.
Mm-hmm.
The denser the object and the faster it's moving, those two things are going to increase the kinetic
More
power
damage
of that punch, right?
That's correct.
Tunguska's low density, like maybe not much more than a piece of ice. That's some of the estimates I've seen, right? 1 to maybe 1.5 grams per cubic centimeter. If you have, I don't know what the density of asteroid 2024 MK is, but if it's a typical carbonaceous chondritic asteroid, it's going to be between 3 and 4 grams per cubic centimeter, right? So what that means is because of the greater density, it's going to carry a lot more punch per volume.
Right.
Okay. So if we just do not consider the implications of density and just assume for ease, first of all, that they're the same density. We leave that out of our equation and we just go by size. Okay, so 2024 has a diameter about 500 feet, which is between 37 and 40 times more massive than the Tunguska cosmic object. Now, if the Tunguska cosmic object was 15 megatons, which is pretty much, I think that's the the power of that impact that most investigators have honed in on, 15 megatons. And that's what I've been using in lectures for the last couple of years. Well, let's assume 15 megatons times 40, right? So now we're looking at about 600 megatons. Now, here's the thing, though. We're talking about an asteroid. So this is probably a factor of 2 or 3 at least less than the power of an impact from an object the size of 2024 MK. You see what I'm saying?
Think I do. Yeah.
Well, because it's an asteroid. So it's like Earth. The difference is, okay, Tunguska is throwing a piece of ice at the Earth. 2024 MK is throwing a rock, a heavy rock at the Earth.
I guess what I'm balancing out is in the thought there's an assumption on Tunguska that it was ice, because you could have a smaller rock, right? It's going to do this with the energy is going to be smaller rock, faster, whatever.
True.
So it could be either or, right? So
well, yes, but I think this is primarily, I think, from I'd have to pull some stuff up here on this to get, but I think it's primarily through an analysis of the pressure pulses.
Okay.
That they're able to reverse engineer kind of and realize that was a lower density object. Because see, think about this. If it was a smaller but denser object, like a lot of
might have made it. Yeah, might have made it farther.
Probably would have made it. Yeah.
Yep.
Now, those are the kind of reports, excuse me, Chuck, that could dispel. Every time this comes up, I read the comments and people want to bring up, oh, well, that was an experiment from Tesla. But people just don't know about all this research that was done, like you're quoting here, these pressures that they could even determine the composition of the material, right? Is there more ways to easily dispel people that want to bring that up?
I mean, there are microspherules embedded in the soil and in the trees. Right there.
There we go. Yeah.
I mean, it's like, the Occam's razor in science. Start with the most obvious, before, if you couldn't explain it by an impact event. But it seems to me, yes, there are anomalies, no question, and unanswered issues. But for the most part, that event is consistent with a cosmic impact.
Yeah, I was talking with someone earlier today, a friend, and we were talking about if you have a result that you're looking at and that there's a simple explanation, right? Like you said, Occam's razor. If you see someone trying to explain to get to this result with a lot of mental gymnastics, then that's probably not going to be it. It could be, but to me, the chances start simple is better. It's a simple explanation is better.
Right. And then the personal stories of eyewitnesses, people haven't found those either. So yeah, I can list those in our description here, prior episodes of Kosmographia, where Randall goes into pretty good detail about
the stories.
Quite a few of those that are just gripping and, quite a few sound straight out of the Bible, biblical scrolls and, all kinds of things. So yeah, this was an object came in from space. So
and I was wondering if you guys have you ever heard the space shuttle come into off of orbit?
The space shuttle?
No. Yeah.
No.
Yeah. When it's going through, when it's coming in, when it's breaking a sound barrier, it's 2 cracks in a row. It goes like that. And it's interesting. It's twice. I've heard it.
Not. Okay.
Yeah. Yeah. At least from wherever I was, but it was a very definite, that it was distinctive. And I was thinking about that earlier when we were saying, they heard 2 booms. I don't know. It's so many variables, right? That's where I look at it. But it's and Randall, did that 2024 fly by like on the anniversary day, or there was National Asteroid Day or something like that, and that's when it was closest or something, or that's
last year, wasn't it last year?
Yeah, something like that. Yeah.
Well, the 29th is right in that window of the Taurids, right? Yeah. Which is what 2 weeks or more. But it peaks on the 30th, and that is now International Asteroid Awareness Day. For I don't know, maybe that started on the 100th anniversary of Tunguska, or maybe it was right before that. But yeah, June 30th is that day annually. Yeah,
and that's another thing when you're talking about, you have a result, this happened, and you see these right around that time of year.
Right.
Add that to it. Yeah.
Well, in June 25th of 2023, there was a near miss. 2023 MU2 flew by the Earth at over 2,000 miles per hour, but it was pretty small. It would probably have exploded in the atmosphere. It was a little bit smaller than the Chelyabinsk object of February 13th, I believe,
Yeah.
2013.
Yeah, I don't know offhand.
Yeah,
15.
you're supposed to be knowing those kinds of things here, Chuck.
Sorry. Sorry
yeah.
to let you down.
So that was on June 25th. So now the Taurid meteor stream, one of the things about it, it's now quite diffuse. So age of a meteor stream is going to be directly related to how diffuse the stream is, because a young stream will still be not uniformly distributed around the orbit. There'll be clumps. The longer and the more it orbits, the more diffuse and uniform, homogeneous the orbit becomes.
Yeah.
So the Taurid stream is fairly homogeneous. However, within that stream, there's probably a lot of big stuff still lurking that we haven't discovered yet.
I can get behind that idea.
Yeah. So the other thing that came up here that I thought would be interesting to talk about for a moment. Let's see here. I just had it. Yes, this is Michael R. Rampino is somebody whose work I've been following for decades. This came out in Global and Planetary Change this year. Let's see if I can see how recent.
Now, is this a new paper?
This is a new paper.
Well, maybe we ought to take a break or finish up a little bit. I want to add a detail in there, and then maybe that'll get you going for a few minutes. Then we can take a break before you start in on another paper.
Sure, man. I'm easy to.
Well, just to jump back, you mentioned the Antarctic impact from 2.5 million years ago, right? And that being close to 2.6, which is the Pliocene-Pleistocene transition. But just to make it more clear to people that are maybe newer to this podcast, right? The Pleistocene, that transition is when we started into this cycle of ice ages.
Good point.
That's been going on.
Yeah,
right,
there was a major. Yeah, a major
so that's something we really pay attention to here.
Yeah.
So whatever that was, or combination of things that initiated that first ice age, and then we've now been through 24 or up to 40 possibly glacial, interglacial cycles, and we're presently probably in an interglacial. Nothing 100% says that we're out of that 2.5 million year
trend.
That's my belief. I think we're in a relatively stable interglacial. That's what I think.
Wait, pause for a relatively stable interglacial.
Mm-hmm.
And how long do you expect this stability to last?
Past lunch tomorrow, that's for sure.
Well, we're hoping at least that.
Let's wait till after the tour.
Yeah.
Well, what I would be going on, and we can pick this up after the break, is that if we look at interglacial intervals, let's say throughout the Wisconsin, we don't find any as long as the Holocene.
It was wild. It was Wild West then.
Yeah, and I mean, the last one, which we thought was the analog for the Holocene, the Eemian, also looks like it was pretty dynamic, but it was actually quite a bit warmer than the Holocene. And I've covered that in some newsletters and things.
For sure.
So if
people need to know that.
Yeah, and if people aren't subscribed to the newsletter, they need to go ahead and do that, because every month I put out cool stuff.
It is good stuff.
It is good stuff.
All right, yeah. And you can get that at randallcarlson.com, right? Videos, podcasts, Randall's new podcast, Squaring the Circle. Past episodes of Kosmographia, tours and events, updates on all that on the monthly newsletter he's saying. But yeah, all through randallcarlson.com. And there's also updates on the tours. So we've got one coming up. It'll probably be full by the time this comes out, but you never know. There's waiting lists. Some people have to drop out right at the end. So if you want to go and are able to, go ahead and sign up and get on the list, and maybe you'll drop in with us right at the end. But always check in. There are announcements on the newsletter and through the website.
The first trip that I ever came on, that's how I got on. I kept trying, and someone had to drop, something happened personal, and I got in.
Okay.
Yeah, it does work.
Perfect. So yeah, Chuck's been to the Scablands with us, been to the Montana Lake Missoula tours, been to, I guess, both the Cosmic Summits.
Yes.
Been out to Sedona when Randall did some conferences. Yeah, so
Jeez.
appreciate your support there, Chuck, and good to have you here. Let's take a break, and we'll get back into whatever the Michael Rampino paper is. What do you say,
Yeah.
Randall?
It's a good one.
All right, break.
Okay.
Great.
I'm ready anytime.
If y'all are up for it, we're into it. We're still rolling. Welcome back. We had a good break. Hope you took a nice break for yourself there, and going to get back into it, see what work of Michael Rampino has to say, and then also there's some megaflood going down the Yangtze River. Is that right? We're going to get into a little bit also
Yangtze.
later. So
Yeah.
but yeah, just a reminder. Tours always in the works. Find those at randallcarlson.com and sign up for the newsletter. randallcarlson.com/newsletter makes it easy. All those links always in the description for the video. I know a lot of people look on mobile. You got to make an effort to find the little thing to drop it down. But yeah, I include all these links, try to make it easy for everybody. So check those things out on randallcarlson.com.
Yeah. Okay. So Michael Rampino is somebody whose work I've been following for years, actually decades, maybe even since the late 70s. He's been in the forefront of, I will say, the revival of catastrophism. He could be classified perhaps as a neo-catastrophist. His work in impacts, in climate change, in volcanism, mass extinctions, and the correlating of all of these things, I think, has been right at the core of this shifting paradigm of Earth history. So in 2023, and then a few months ago, he had two new papers, both of which are quite interesting. Okay, the first one we'll look at is, and it was in Global and Planetary Change. Title of the article is 16 mass extinctions. Now, those are the big ones, the knowns. The really 5 big ones and 10 or 11 more smaller mass extinctions, but still big enough to be clearly discernible in the fossil record. So 16 mass extinctions of the past 541 million years, correlated with 15 pulses of large igneous province volcanism, and the 4 largest extraterrestrial impacts. So in his abstract, he says, we find that large igneous province, or LIP, right, large igneous province, LIP, volcanism, mostly continental flood basalts, and that's abbreviated the CFBs. CFBs, Chuck, are continental flood basalts. You earlier mentioned the Siberian traps.
I did.
That would be a CFB.
Well, Deccan Traps I was talking about too.
Oh, you were talking about the Deccan Traps.
I was talking
that
about Deccan
too
Yep.
would be a CFB.
Yep.
Okay. So CFB is continental flood basalts, and LIPs are large igneous provinces. Okay. So we find that large igneous provinces, mostly continental flood basalts, along with the largest extraterrestrial impacts, show significant correlations with mass extinction events in the Phanerozoic geological record. And I think that this is going to be the trend that continues as we learn more and we refine our dating. We're going to discover that all of these kinds of events are intricately interconnected. And like you said earlier, it's not a simple straight line connection.
Right.
It's a complicated connection, but they're still connected. The fact that it's not a simplistic straight line connection doesn't mean they're not connected. The ages of the 6 major marine mass extinctions with more than 40% extinction of genera of the last 541 million years is the end Ordovician. That was one of the geological periods, the Ordovician.
Mhm.
And this one was centered right around approximately 444 million years ago. Easy enough to remember, 444, 444 million years ago. This was followed by the late Devonian, which is clearly a multiple impulse event. This has been known for a long time that the end Devonian was a protracted series of events.
Yeah. Age of the fishes, known as.
Mhm.
Yep.
Approximately 372 million years ago. And then the Guadalupian at about 259 million years ago. Notice it's close to 260 million years. The end Permian,
Mhm.
this was probably the greatest mass extinction in life history on Earth, which was dated at 252 million years ago. And then the end Triassic, which just preceded the Jurassic. Now, everybody knows about the Jurassic now, right?
Yeah. Can't get away from it.
The Mesozoic was the Triassic, Jurassic, Cretaceous. Now, most of the dinosaurs that appear in the Jurassic Park movies are actually Cretaceous dinosaurs. However, somebody along the way, some Hollywood marketing guy, or maybe it was, what's his name? Probably the author of the book, Michael Wright, right?
Mhm.
Didn't he write Jurassic Park?
Yeah. It sounds a lot better, doesn't it?
Yes, than Cretaceous Park.
Yeah.
Jurassic Park, yes. So that was the decision. Well, even though it's mostly Cretaceous dinosaurs, we'll call it Jurassic Park. So the end Cretaceous was 66 million years ago. I left one out, which was the end Triassic, which ended the Triassic, was right there at that boundary, launched the Jurassic. That was 201 million years ago. Okay. So it says that those mass extinctions are significantly correlated with high quality uranium and lead zircon and argon 40, argon 39, argon ages. We don't necessarily need to get into the dating technologies. It'll be an interesting thing to talk about at some point.
Yeah. That'd be neat.
But those dating of 6 continental flood basalts, and those 6 basalts are the Cape St. Mary's, the Valais, the Amishan, which maybe is in China, the Siberian,
Mhm.
and the Camp, which is the Central Atlantic Magmatic Province, and the Deccan Basalts. Okay. So the mass extinctions also coincide with stratigraphic anomalies representing proxy evidence for the synchronicity of the extinctions and the basaltic volcanism. Furthermore, ages of 6 minor extinction events, which involve 15 to 25% of the marine genera. Okay, so that would constitute a minor extinction event. Let's say 1/4 of the species disappears rather than more than 40%, right? Which is now a major. Okay, so that one of those happened at 94 million years ago, 124 million, 134 million, 183 million, 290 million, and 510 million. And they also coincided with 6 well-dated continental flood basalt eruptions: the Madagascar, the Halep, the Piranha, Etendica, Karoo, Farrar, that's in Australia, the Pinjal and the Karajindi basalts. Now, I haven't studied those, so I don't know really where those are at, but I will. I will remedy that
Make a note.
deficiency in my knowledge. At least 3 minor extinction events at 145 million, 215, and 227 apparently occurred close to times of oceanic plateau volcanism in the Pacific Ocean. So major and minor marine mass extinctions, mass extinction episodes at times of continental flood basalt eruptions were commonly accompanied by ocean anoxic and eosinic events, meaning decrease in oxygen, increase in acidity. High atmospheric CO2 pressure, increases in ultraviolet radiation from ozone layer destruction, which we were talking about with Tunguska, and pulses of high ambient temperatures, providing potential immediate causes for the mass extinctions. So yeah, the foremost recent major mass extinctions, 65 million, 201 million, 252 million, and 260 million, and a minor extinction of 290, coincided with the ages of continental flood basalts and with concurrent mass extinctions of non-marine vertebrates, indicating global-scale volcanogenic environmental crises on land and in the sea. There we have it. What appears to be showing up here is correlation. Now, he hasn't mentioned the impacts yet. Let's see here. Yeah, okay, so the age of the abrupt end Cretaceous major mass extinction overlaps with the age of the Deccan eruptions, but is exactly coincident with the very large Chicxulub impact.
There you go.
180-kilometer diameter crater, possibly the largest terrestrial impact of the last 3 billion years. The ages of the next 3 largest well-dated Phanerozoic, let me define that. Phanerozoic is the time of visible life, essentially, of visible life in the fossil record. So the ages of the next 3 largest well-dated Phanerozoic terrestrial impact craters, which include the Papagai, which is in Siberia, or Popagai, the Morokwang. Where is that? Brad, we want to look that up while we're Morokweng, and the
South
Manicouagan.
Africa.
Must be. I believe it is. But get this, Popagai, we know about that one because it was roughly correlated in age with the Chesapeake Bay crater that spewed tektites all over the southeastern United States. Manicouagan, we know what that one is, right? You know about that one, Chuck? Manicouagan?
No, it's Canada.
All right. Well, let me just show you here. All right. I will do a quick share screen while we're looking at that. And here, no, not that one, this one.
Buried
here
beneath the
is-
Kalahari Desert near, South Africa, Northwest
South
Province.
Africa, right.
Yep.
So we're seeing this here, Chuck?
Yes, I do.
Okay, so that is the Manicouagan crater up in, let's get it out so you can see where it is.
Ooh,
Oh, there you go.
the
Plus Canada.
off-seas canoe trip.
Yeah.
Yep.
Yeah, I had it. Yeah. It's up by.
But yeah, there's a level out there. You can see the bigger circle around that
Yeah.
inner structure.
Look, right here. You can follow it right here. You see it? Can you see this?
Yeah. There's a
Chuck?
good amount of mining that goes on up that way.
Yeah. Probably. Now, I don't know about that. I mean, I know there's a lot of mining at Sudbury.
Yeah, there is for metals, but there's there up that I believe that there is up that way.
Let's
where
see.
we were.
Sudbury is,
No, that's farther north than that.
Yeah.
That's way too far south. You want to go
Into the
quite a
Great
bit farther
Lakes.
north.
there's Sudbury.
That's Lake Simcoe there on your left. So you want to go up,
Yep.
see Go straight up. Yeah, that's Simcoe. All right. So then go straight up and that's right. And then you're gonna go up a little further. And Sudbury's up in that area.
Yeah.
But if you look to
Oh.
your yeah, you're up in there.
Are we talking the town or the impact?
Mm. I'm trying to
All the
recognize
mining's
something.
down in it, right?
Yeah. Well, there's the nickname for the Sudbury is a big nickel, right?
Uh-huh.
But I think there's plenty of evidence for some
Lake
old
Saint
impacts on
Jean.
Canada.
Oh yeah, there is. So yeah, so there you can quite clearly see the outer arc right here.
Mm-hmm. This is
On the south
really
side.
interesting. That's a trained eye looking at this, right? It I know there's people right now watching this on TV. You're going, what is he looking at? And it's like anything else. Once you start learning how to see them, then you can start seeing them. It sounds funny like that, but same thing with things called lineaments. You'll see straight. Nature really doesn't cause straight lines. You see straight lines, something's up.
Uh-huh.
And these things here are similar.
Well, what you have here is this is a central uplift. This is actually an artificial reservoir, I believe, if memory serves me correct. I think we had a dam. Right, yeah, here we go. So we have a dam down here.
That's quite a
And
structure.
let's see other,
There's a couple more there, yeah.
a couple more here.
No,
Yeah.
those are just
Oh.
artifacts.
Or is that just artifacts of it?
from
Oh, those were taken in the winter.
different timing.
Yeah, that was
of
probably taken in the
images.
winter.
Yeah, right.
Yeah. I'm surprised it's all artificial. I didn't think it was, but
Well, the
What's that,
topography
80
is natural.
miles, Randall?
yeah.
About 50 miles.
Oh, 80 kilometers. Sorry, yeah, 50
Yeah,
miles. Yeah,
So,
Canadian.
and that's the inner circle. The outer circle, again, I don't know. Let me zoom it back here. You can see it. If you look, I think you can see. Can you not see this outline? It's faint, but it's there.
Oh, I can see it.
Oh, yeah.
Yeah.
Yeah, I can see it.
Well, and it's equidistant from the, it's concentric.
Mm-hmm.
Yeah, if you just kind of
And
relax and take
this-
it in, you can see it.
This could be a ring here too, right there. You see this transition?
I do.
Sure.
Yeah.
So yeah, you can check some of the elevations there if you were in Google Earth.
Well, I am in Google Earth, but I didn't do Google. We could check elevations if I get out
No,
of
well,
here.
that's kind of a little
I do have Google
project,
Earth
but yeah.
Pro. So yeah, that would be an awesome canoe trip to spend a couple of weeks paddling this circuit here. And there's some interesting outcrops by Manicouagan. Yeah, that would be very interesting to do. Maybe summer of 2025.
Yeah, I lived in Canada for a while, so I've done some of that canoeing, not right there, but in areas near there, and it's beautiful.
Yeah.
We've been warned about the bugs.
Yeah, it's the provincial bird. Yeah, for
Now,
yeah.
I've often looked at this right here.
Yeah.
Ever looked at this, Prince Edward Island, and looked at the
Good shape.
yeah, look at this. It's half of an arc. And then you look at this here, you can see perhaps a remnant of, this would have been really old. And then you could have a highly eroded central uplift ring here. It reminds me of Clearwater Lakes. And let's see, Clearwater Lakes is
A little farther north. Yeah, you're almost to them.
there we go. There's Clearwater Lakes.
There's another one. That's right there. There you go.
Now look at this. This, could this be Prince Edward Island? If you cut this in half, you've got that's I believe it's Newfoundland, right?
Yeah, Newfoundland.
Newfoundland. Okay.
Newfoundland. They like to, yeah.
Yeah.
Yep. No, it's a there's a lot to be seen there. You can actually see when the sea levels were lower, you can see the St. Lawrence River channel cutting through there. That's making the outer part of your most northern shape that you were pointing
Yeah,
out.
and look
Right,
you can trace the current flow right through here, because this was a major conduit for glacial meltwater. And look at this, and I would guess that's what created this trough right here. So you see that? Look, you've got an underwater, it looks like an underwater escarpment right here.
Yeah, I think that's a former river valley there.
Yeah, yeah. Coming down this way. Look at this. You can trace it right on down.
Yeah, just think of all the archaeology around there.
That's huge.
Yeah, it is. It's a huge meltwater. And
It's as wide as the Great Lakes.
you look at this. We've thought this has been a potential impact site right
Yep.
here.
Lake
Lake
Saint
Saint
Jean.
Jean.
Yeah.
So Saint Jean, yes.
Saint Jean.
And an impact, a melting event, and a catastrophic outflow right here. And if I zoom out, and then of course there's Lake Nipigon here, and it's in a circular basin. If I go to
Yeah.
Google Maps, and I'll go to terrain view.
You
Google,
got those inner islands, kind of like the Clearwater Lakes that you were showing also.
yeah, Google Maps.
Yeah, that's very curious there for sure. Yeah, we've got an older video. The very first tour we did, Contact at the Cabin. You did a presentation on that, and you can find that on the YouTube channel.
Yeah. Okay, so if I zoom in here, I would speculate that this is a prime candidate for an impact right here. You've got
Well, and adding to that, to me, what makes more likely is if you go up to the northeast a few hundred miles, then a few hundred miles more, there's a pattern, right? Those lakes are all in a row.
which ones?
If you go Nipigon, let me see. Here we go. There's a bunch of there's a set of lakes
You said to the northwest.
northwest. Yeah, I hope I did. Yeah.
Oh yeah, so you're talking about Lake Winnipeg.
And then you go up right there. There they are. Boom, 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 boom. All right.
Yep. Reindeer Lake,
All right.
Lake Athabasca. But we won't talk about that right now.
No, but I always find that fascinating right there. Yeah.
Yep.
Yeah.
They are aligned.
Yeah, that's one of the things, as Randall knows. I mean, when you're studying geology, you're really training your eyes to look for shapes.
Mm-hmm.
And I don't know where we were, Randall. I think we were in, I don't know, it could have been Montana or something like that. But I remember standing there talking to you. We were talking about looking at some kind of geologic features, maybe over the Columbia Gorge or something like that. And the discussion evolved in how could you not see it, right?
Mm-hmm.
And it's just because you're used to looking for it.
So here's where we're going to be traveling in September. We will be coming down out of Spokane, right up here, and then we will be hitting this interesting thing right here, Steptoe Butte State Park. Were you with us on a Steptoe Butte? You were, weren't you?
Absolutely. Yep.
Yeah.
Yeah. Beautiful day too.
Good. And then, yeah, look at that.
Yeah. We had a nice sunset from up there.
Look at that.
We were there that springtime, right? We were there in the fall.
Yeah, this is the springtime.
Yeah. Yeah. You can see the relief a lot more.
Yeah. And it's nice to get there at a low sun angle. So then we are going to follow down here to Lewiston and Clarkston, and we're going to go visit a place right in here. Let's see. I believe, let's go to the satellite view. Yes, we're going to visit. This is it here, isn't it, Brad?
Yes.
Yeah. So
Atlas
we
Sand
are,
and Rock.
yeah, that is a rock quarry. And this is the place where the Great Bonneville Flood met the Great Missoula Flood. Because the Missoula Flood, we can see this channel right here. It came down, and when it hit the Snake River Valley, it reversed the flow of the Snake. And you had this, I guess you could compare it to a tidal bore, and it worked its way all the way back upstream to Lewiston. And it came all the way down the Snake, backed up into the Tammany Creek up in here. And that was pretty much as far as the Missoula flood got. And then the Bonneville flood started way down here. Get this, in Great Salt Lake area. And this is the remnant of the salts you see here are the remnants of Lake Bonneville, which burst through the northern rim of the lake. And let's see here. Yes, right. This was the route. 15 here follows the route of the outburst flood. And it burst out right here, carved out the channel that American Falls Reservoir right here is in, and then flowed all the way across, drowned, submerged a lot of the Idaho River plain, all of this, and then ultimately made its way north and up through Hell's Canyon, right in here.
Yeah, it's some spectacular scenery with something to learn while you're looking at it too.
Yes. So we will see Bonneville flood sediments, but we of course aren't going to follow the route of the Great Bonneville flood, but we're going to see juxtaposed Missoula backwater, slackwater sediments and the high energy sediments of the Bonneville flood. Because the difference here, Chuck, is that this is the backwash of the Missoula flood, and it's the downstream flow of the Bonneville flood. And they met right there, just south of Lewiston on the so-called Tammany Bar, which is this thing right here, and built this.
Mm-hmm.
So we're gonna explore that. We're gonna have special permission guided tour of the rock quarry. And then we're gonna head on. Oh, let's see. We're gonna go to down here. We're gonna follow this down to the Tri-Cities area, which is all the way down here at Wallula Gap. And Brad's got some special stops for us that he's arranged that are definitely off of the main tourist tracks. We will go through Wallula Gap right here where the gathering of all of these waters occurred. You can see the Cheney Palouse flow coming here. 90 follows it quite a ways. You can see the Telford flow right here. You can see Grand Coulee here. You can see Moses Coulee here. And then there was evidence of catastrophic flows coming down the Columbia. So all of these were contributing water that flowed down and ponded above Wallula Gap right there and formed what the early geologists who discovered the evidence for a ponding of water there, they called Lake Lewis. And then the water discharged under tremendous force through Wallula Gap and spilled through the ridge here and formed a lake, which is called Lake Umatilla. Lake Umatilla Rock up in Grand Coulee. And then it comes down here and pushed its way right across the Cascades. So we'll be following that route. And this will be the first time we've done an official tour following this route. This is like number 3, phase 3 of the trips. That's why there's too much to see. So we've focused the Scablands. We've separated that from western Montana and northern Idaho. And we've separated that from this trip that we're going to be going on here, because we're not going to go all the way to Portland. That was my latest understanding.
Well, some people are going to fly out of there, so you'll get to emerge from the gorge and see the debris fan, I guess. Right?
Yeah.
Portland sitting on hundreds and hundreds of feet of sediment that's been washed through the gorge.
Yep.
So yeah, some people will get that far, but some people will return back and do round trip flights out of.
Yeah, that's the only segment. It's the only segment I have been on. So hopefully I'll not this time, but kind of missing it,
Well,
yeah,
we got Chuck with us here. Let's get back to the multi-extinction events there.
Yeah, and I was and along those lines, you're talking about outflows. I think there were some papers on on some big outflows with, but caused by different, landslides and whatnot too. I think we were talking about that earlier.
This is kind of a cool graphic here. Let's enlarge it and take a look here at what we got. So here is a graph of the mass extinctions. Like here you can see the percent of genera over on the y-axis. So you can see here the greatest spike is the end Permian.
Yeah.
And that's associated with the Siberian traps. Now, here's a little something that's quite interesting. The outflow point of this large igneous province, the Siberian traps, when the Tunguska object came in, it exploded directly over the paleovolcanic center that was the outflow of all of the, almost as if it was aimed at it. It was directly on top of it, which is interesting, which made one Russian scientist wonder if possibly the event was endogenic and having something to do with an internal phenomena related to the ancient volcano. Anyways, so this, here are, and then look, the red stars. See, those are, look, impacts. There's the Chicxulub, perfectly timed with this. Here's this impact, an impact here, an impact here.
I think that over time there'll probably be correlations to
Yes. And you'll notice that the correlations with the impacts are the younger ones, not the older ones. Because obviously the more time that passes,
can't find it. Yeah.
You can't find it, right?
Yeah.
But what this suggests to me is if it probably is not just a spurious correlation, that there is a relationship between impacts and volcanism. And those two things, it could be that the impacts, well, I mean, how could a major impact not have seismic and volcanic consequences?
And that's what I was getting at earlier with the, for instance, even, there's thoughts about at the antipode, right? The spot opposite the planet where it hits, because the shock waves go around and meet, just like if you're in a lake, you could make a wave stand up by making the right motions, and that fractures the crust in a big way. And you start getting those, and those volcanic, that activity went on for a long time for some of those, which has great effect to the planet.
Well, I think
life on the planet.
Yeah.
Mm-hmm.
Yeah. So we have almost a straight line correlation here. Look at this.
Yeah.
So here's your extinction events, and here's your continental flood basalts here. And then you've got your impacts, right? So let's see what it says. Ages of 12 continental flood basalts and 12 correlative marine extinction events, which are the filled dots. Correlated plus the correlated North Atlantic igneous province and the Paleocene Eocene thermal maximum, which is the unfilled dot. So there we go.
Tells an interesting story, doesn't it?
Yes, it does.
Yeah.
It tells us that our planet is part of a much, much larger ecosystem.
Yeah.
That we have to start thinking big scale. We've gotten around that by, everybody will acknowledge that the sun is a critical player obviously in the environment and climate of Earth, but it's been downplayed deliberately for political reasons. And it's been convenient to do that because of the fact that for so many decades, the sun was assumed to be a relatively stable star.
Yeah.
Hence the term the solar constant. So if the sun's output remains constant, it can be disregarded in terms of its effect on changing climate down here on Earth. However, we now know, after a couple of decades of satellite observation of the sun and looking at other sun-like stars, it's more and more looking like there's evidence that's pulling us away from the stable sun idea, especially now that we're showing up episodes that look like they could be the imprints of, solar storms and coronal mass ejections and so on the Earth. The carbon-14, the beryllium-10, which implies destruction of the ozone layer, which could be impact, or it could be the result of overwhelming by the sun. So there's a lot to talk about there.
Yeah, there is.
Yes.
Yeah, if you're measuring over a very, very short period of time, things look stable, right? You measure over a long period of time,
Yeah.
it doesn't look. It looks, it's a different perspective, and you have to take that into account.
Okay, then the other one by Rampino and his two colleagues was in Earth Science Reviews. This is from 2023. Let's see, it was available online the 25th of September, 2023. So it's pretty relatively new. Cycles of 32.5 million years and 26.2 million years in correlated episodes of continental flood basalts, hyperthermal climate pulses, anoxic oceans, meaning oxygen deprived, and mass extinctions over the last 260 million years. Connections between geological and astronomical cycles. Notice here, again, the 26.2, how close that is coming to 26 million years. And 26 million years is basically 1,000, what we might call great years or precessional cycles. And then we go 260 million years. So 10 of those cycles gives us the 260 million years. So 260 divided by 10, we get the 26.2 cycles. And then divide that by 1,000 and we have the precessional cycle. And 4 times the precessional cycle brings us back to 104,000 years ago. So we need to look and really figure out what went down 104,000 years ago. So the Eemian lasted from 116 to 129,000. So it was the last period of comparable interglacial warmth, and it was right at about 13,000 years. However, there was a couple of major interruptions occurred during the Eemian that were much larger than any of the eruptions that have occurred during the Holocene. But it lasts, like I said, it's now dated from 116 to 129,000. So 13,000 years of warmer than present climate was the Eemian. And sea levels 20 feet and more higher than now. So I think this is interesting. These correlations, is what we're learning about as we get more familiar with the big picture.
And the idea skip over the one that we talked about earlier, just the Eocene Pleistocene, or Pliocene Pleistocene transition at 2.6 million, right?
Yep.
So that was in that sequence too. So do you guys know, maybe it's in there, but it seems like I've heard that our time to circle around the entire galaxy is 260 million years.
I think it's pretty close to that. A galactic circuit.
Yeah.
I think you're right. It'd be easy enough to
yeah.
find out.
Yeah. Have you heard that, Chuck? That
yeah, I
mind.
I can't say absolutely that I have that data, but it leads you to the belief that there's a pothole somewhere on that road that we come across every once in a while, right?
Right. And then it's also, phi squared, right? 2.6180. It's kind of strange.
It's interesting. I'm always, when you see me I'm not being purposely, well, I am kind of being purposely evasive. It's hard for me to commit to an exact number.
Sure.
I always round almost everything, especially when it comes to these types of measurements. They're generally, you can use them, you could talk about them, stuff like that, but I don't have everything is constantly being refined, and those times are being refined, and new information comes to bear. So when you see me doing that, that's the way I am.
Well, I would like to see more or hear more scientists say that.
Well, if you're going to be a practical one, I'm
things are
actually known for
constantly
being practical.
refined.
Yeah.
Constantly being
Otherwise,
refined.
it's
Okay, so
you're deceiving yourself.
Here's galactic year definition and detailed explanation. A galactic year, also known as a cosmic year or stellar year, is the amount of time it takes for the sun to complete one orbit around the center of the Milky Way galaxy. This period is estimated to be around 225 to 250 million years.
Okay.
But, I mean, if we're in a period where it's just a little bit faster, I mean, do we assume that that's going to be a steady orbital velocity through the whole circuit? If not, then there's an average, but then sometimes we're going a little faster than the average and sometimes a little slower. If the time that we've measured our movement relative to the galactic center now is just even slightly faster than the average, well, then it'll cause the duration of that galactic year to become less, because we're going to make, So yeah, I mean, it's kind of in the ballpark of 260 million years. So that's it. A trip around the galaxy, a galactic year.
I was just doing some math here. And it's an infinitesimally small number, because we're making the measurements and we're basing them, and I just tried to put it on a lifetime, and you try to see what period of time we've made that measurement on that 260 million years, and it's like there's a lot of zeros there. I can't even. It's like 100 thousandths of 1% or 300 thousandths of 1% or less than that even. So
right,
yeah. So that's why I'm getting at with those numbers. You can roughly get there, but like you say, Randall, there's variables in there. Sometimes a little faster, slower. You can't assume that the Milky Way galaxy is static, right? That's
right.
Everything's moving. Yeah. So I don't know. I like that kind of correlation. We were talking earlier during the break, and another one that I think is interesting too. And we're going to talk about maybe this time or maybe some other time, but we're talking about sea levels. And I always find it interesting that when you talk about a sea level change, and you hear that often on a podcast of 1,000 feet, maybe, and maybe the Earth has adjusted itself, the planet's adjusted itself, but there's a sea level change of 1,000 feet, and people think, wow. I mean, a lot of folks will, if I talk to them, say that's a lot. It is a lot from our perspective, but if you calculate that out in a percentage of the radius of the Earth, if you just do it that. It's 0.0478%. So it would be, 47 thousandths of a percent of the Earth's radius is 1,000 feet of sea level. Put that into perspective. It's not a lot. So these changes we're talking about sound, I don't know, that's the perspective that I have. They are catastrophic for us, for inhabitants, but when you really look at the scale of things, they're small changes. It shows how thin the water is on the planet.
Global terms, the cosmic scale is pretty tiny. So 1,000 feet out of 3,960 miles.
Yeah, that's right. So it's in feet, the radius would be 20,902,000 feet, right? So that would be 0.04. Figure that out.
Are you talking radius of the Earth then?
Yeah, the radius. Yeah, I'm just running radius. Yeah. I don't know. I always like to have things in perspective.
Well,
you got point.
We need to feel any smaller.
Yeah. I came up with 0.00047.
Yeah. You got to then go by 100. I went to a percentage though, so then bump it up. 100. Yeah, so I'd 0.0478. Yeah.
Drop off to
0.00478%. So that's pretty small.
It's tiny.
Now, why are we talking about this? Where did this come from?
I learned how to use a calculator today.
Oh, okay. So one of
Thanks.
the articles, Chuck, that we both read was about this outburst flood event in the upper Yangtze River.
Yes.
Right?
Yeah.
Which was published by a gang of Chinese scientists. Let's see here. I did actually report on it in the newsletter.
Mhm.
And this is what I said. Here we go. Let's see. Make this a little smaller.
And the gang was actually led by gang.
Gang, yes, gang who? This past May, a major geomorphological study was published in the journal Global and Planetary Change. The study was authored by 13 Chinese earth scientists, archaeologists, and engineers. The focus of this study was the history and susceptibility to floods and landslides in the upper reaches of the Yangtze River in China. The Yangtze is one of the Earth's great river systems. It is the longest river in Eurasia and the third longest in the world. Did you know that, Chuck?
Mhm.
Oh, you did?
No.
Oh, okay. Darn.
I probably did it. You caught me by surprise. I could probably sit down and think about it. But yeah.
Okay, well, we know.
Yeah, because I'd have to think where the Amazon falls in that. And then I'd have to
Yeah. The third longest in the world. It heads in the Tangula Mountains of the Tibetan Plateau and flows for 6,300 kilometers or 3,912 miles. By volume, it has the fifth largest discharge of any river in the world. So, in talking about it, the authors say, and I quote, the Yangtze River is the longest river in China, accounting for 1/5 of China's total land area. In its upper course, it is called the Jinsha River. The Jinsha River flows from the eastern margins of the Tibetan Plateau to the Sichuan Basin. There is a marked altitudinal difference of 9,840 feet between the Hengduan Mountains and the Sichuan Basin. So between its headwaters and where it discharges from the mountain into the basin, a difference of 9,841 feet. So that's a pretty good gradient there.
Yep.
The lower Jinsha River has therefore become a key area for the development of hydroelectric power. The conventional flood risk assessment tool used for hydroelectric power stations in this area uses a flood frequency analysis extrapolated from annual maximum flood, or AMF, annual maximum flood volumes. Got it? So we've got however much the record goes back, we look at the average maximum or the annual maximum flood and extrapolate from that to get some concept of what the next larger flood scale would be. In this basin, AMFs, or annual maximum floods, are usually caused by seasonal or monsoonal precipitation, which normally falls between June and October. However, the Jinsha River has been frequently blocked by landslide or debris flow during the Holocene due to the active surface processes and tectonic movements that have occurred in the Hengduan Mountains area. End of quote. Then I say, in other words, the annual maximum flood is based upon observed discharges occurring regularly biannual precipitation with an extrapolation for a 100-year maximum flood. However, the authors cite two flood events that happened in the Yangtze, or upper Yangtze, which is the Jinsha River, in very recent times. This is what they say. Quote, the upper Jinsha River was blocked twice by landslides at beige, which B-A-I-G-E, you can look it up on the map, and gives the coordinates, which I've done here. And I might have a graphic I can pull up. On the 10th of October and the 3rd of November 2018, resulting in extensive damage to downstream areas. The water discharge rate of the outburst flood from the dammed lake could have been as much as 10 to the 5th cubic meters per second. Okay, got that? 10 to the 5th cubic meters per second. So if I go 10 to the y to the 5th, that's 100,000 cubic meters per second. Now, a cubic meter is about 36 cubic feet. So I'll go times 36, and that is about 3,600,000 cubic feet. Okay, we'll get a handle on that in a second here. So the point here is this. 3.6 million cubic feet is, as in their words, much stronger than that of the AMF, the annual maximum flood. However, the history and magnitude, get this now, here's the problem. The history and magnitude of outburst floods in the Jinsha River Valley remains largely undocumented. So there was a flood in this river that they want to build a lot of dams on for hydroelectric power. They're making an assumption about annual maximum discharge and extrapolating from that up to a 100-year flood and using that as their parameters for their dam design. But here, just 6 years ago, almost 6 years, in October, November of 2018, there was this landslides blocked twice and created, as a result, these outburst floods. Because now you picture the landslide falls into the valley. It now creates a temporary dam. The water rises up. I'm not sure. I believe the dams failed by overtopping. So, in an effort to remedy this deficiency, the authors explained that, quote, in this study, we have attempted to document outburst floods during the historic period by conducting field investigations into and the numerical dating of outburst flood evidence found in and around the first bend area of the Yangtze River. And I can show you where that is if we want to get back to Google Earth. So that was the end of their quote. And then I come back with this commentary. It is important to note that greater than 10 to the 5th power cubic meters means greater than 3.5 million cubic feet per second. To get a basic concept of what this means, consider that the average annual flow of the Mississippi River is just under 600,000, or about 500,000 cubic feet per second in its southern reaches. During the Great Mississippi Floods in the summer of 1993, the peak discharge at Boonville, Missouri exceeded 700,000 cubic feet per second, and at St. Louis, Missouri, the peak discharge topped out right at 1 million cubic feet per second. So the outburst flooding along the upper Jinsha equaled 3.5 times the flow of the second greatest flood ever documented in historical times on the Mississippi River. That's a lot of water to be gushing down a steep mountain valley, and yes, it is much larger than the annual maximum discharge.
It's a lot.
So they're planning to build 23 hydroelectric power stations along the Jinsha River. 7 have already been built. So, using state-of-the-art data sets, a study by Liu et al. Published in the journal Engineering Geology in 2021, they developed an inventory map of landslides along a 2,000-kilometer corridor, or about a 1,200-mile reach of the Jinsha River. They processed more than 360 SAR infrared satellite-based images These authors were able to identify, get this, more than 900 landslides along the full reach of the river. As Hu et al. Point out from this paper, such landslides, quote, are potentially related to seismic activity, heavy rainfall, and high slope gradients. Now, obviously, there could be correlations between seismic activity and heavy rainfall.
Mhm.
If you have heavy rainfall, really heavy rainfall, yeah, you're going to get landslides. If you get moderately heavy rainfall, you might not get landslides, but if you throw in a seismic event, then you're going to get landslides.
Even if it's a smaller one. Yeah.
Yes.
Because it's, yeah.
These landslides risk blocking the river, threatening the safety of these hydroelectric power stations. Such blockages could lead to dangerous water buildup and even catastrophic outburst floods, threatening both the facility and the downstream areas. End of quote from the paper. Earlier studies had identified the presence of lake sediments at 13 locations along the Jinsha Valley. In other words, there were lakes, right? Because if you've got a dam, the water piles up behind it, it creates a lake. Until the dam bursts, you now have a lake. So you can begin to correlate these suites of evidentiary features.
Mhm.
You've got a lake, you've got perhaps the remnants of a dam, and then you've got extreme erosion below the dam. Then you've got sedimentation below that. And you can begin to reconstruct these events. So what did they say there? They found lake sediments at 13 locations along the Jinsha Valley.
Yeah, lacustrine sediments. Yeah.
Yep. In other words, there were lakes in these locations, and the presence of lakes implied that something had to have dammed the river. By employing high-resolution Google Earth imagery and 30-meter resolution elevation data from the shuttle radar topography mission, along with the aforementioned work by Louis et al., these authors expanded upon the earlier work by identifying exposures of fluvial outburst flood sediments. They worked out the altitude above sea level, the boundaries of the formations, relative distances between the landforms, different types of landforms such as fluvial terraces and deposits of flood-laid sediments. Sediment samples were collected from flood deposits for optically stimulated luminescent dating. In addition, a total of 7 charcoal and nutshell samples were processed for radiocarbon dating. But you know what? There's really an interesting twist to this story. Okay, so there were earlier studies by this team who identified 2 fluviolacustrine sedimentary sequences, right? Lacustrine, lake, fluvial, flowing water. So put those together in one word, you have fluviolacustrine, implying the handiwork of both lakes and moving water. So they identified 2 fluviolacustrine sedimentary sequences in the Shigu Basin. The term fluviolacustrine means produced by both flowing water as in a river together with a lake. The presence of 2 distinct sequences led them to assume that the Jinsha River was dammed twice and had 2 associated outburst floods. The earlier of the 2 floods could not be dated accurately, but fell somewhere between 7 and 20,000 years ago. And the later flood, according to radiocarbon dating, occurred about 1,500 years ago in the late Holocene. This lake was estimated to have achieved a volume of about 28 or more cubic kilometers, which is about 6.8 cubic miles of water. Okay, so the earlier team, or the same team by Hu et al., discovered that the outburst flood sediments were unconformably deposited on top of a cultural layer. So this is interesting. And unconformity. Well, what does that mean? What is an unconformity? Well, it means that there was something removed, and then the flood was deposited on top. Unconformably means that the flood sediments were buried on erosional or non-depositional surface, separating two types of strata of different ages. This
Right.
indicates that the deposition of the sediments was not continuous. As the authors point out, this sequence implies that, quote, the outburst flood event occurred suddenly on one of the four terraces flanking the river. And I think what I'm going to do is you're seeing this. Which screen are you? Okay, we can go down here. This shows where it is. Okay, so here is where they did the analysis. Here's the Jinsha River, and it comes and it makes this big bend here. And right here where they've got the hatch marks, that's where the lakes were. Or at least, yes, so there was a dam right in here somewhere. Okay, so yeah, the Paleo Dam, they're calling it, is this feature right here. The Paleo Lake area is the yellow area, which would make sense, right? Here's the dam, and behind it is the lake. And then down here, the red is the megaflood deposits. So the dam gave way and the megaflood gushed down this valley. And when it entered this basin, you can see here that you've got a narrow valley, opens into a basin right here. And that is where the flood, where the megaflood deposits were emplaced. Now, what I think I'll do is I'll stop that share and I'll do another share, which is the Google Maps.
Let me fire a question in here. I don't know what's a good time for it, but yeah, the idea of 30 new dams, that's a lot of
Yeah.
concrete sitting
Yep.
in. I don't know what their distance is, but I was watching something recently about the magnetic field and the pole shifting, things like that, and it was saying that there's been so much new construction on the Asian continent, I guess China specifically. I'm not sure how concentrated, but there were so many new cities and so much new concrete that it was starting to destabilize the spin. Is there any way that humans could add enough concrete
Well, let me ask you a question.
regionally to have any effect on the spin?
Okay. Concrete's heavy, right?
Yeah.
They don't travel very far. So if you're making concrete, you're digging up the rocks close by and you're adding cement to it. You're at, lime, and you made cement. So cement and aggregate makes concrete,
Okay.
and you got it from the area.
But I
All you're
like
doing is
that.
moving it from here to there,
Right.
and then stacking it different. I don't know.
Okay.
I'm not importing bags of, I'm not importing concrete from too far away.
Makes good sense right there.
Yeah, that's the way I'd look at it. Yeah.
Yeah. I was like, what? And they
I mean,
were-
locally you could get some, deformation or something like that, you would assume, but
Right.
I don't know. And that's, I think, where Randall's headed here with these dams. It's like, sounds like dominoes in if it's on the wrong day.
Yeah. Yeah. All right. Thanks.
Then here's where it starts getting interesting. Yeah, here's a Google Earth. Let's enlarge this. So the dam was right in here where the blue arrow is pointing to. Then the lake backed up around this bend here, right? That's what we just saw looking at the previous graphic. And down in this basin is where the megaflood sediments were deposited. Once that water gushed out of the channel here, the narrow constricted channel, it spread out, slowed down, and then it dumped its cargo of sediment right into this Xingu Basin right here. Okay.
Hey, we're going to see something analogous on our tour here. The landslide in the Columbia Gorge there at Bridge of the Gods. That's going to be one of our stops on the finale day or the penultimate day. Yeah.
This is where, to me, it starts getting really, really interesting here is
And we are getting a little late on this end. I know Chuck's got some traveling to do early in the
Okay.
morning. So,
Well, I can wrap this up
oh
within
yeah.
about an hour and a half. So,
You let me know how it goes. Yeah, I'm gonna have to cut out of here pretty soon. So
okay.
bumping
well,
up to
we,
midnight over
I
here.
mean,
Yeah.
what I'm going with this, we can conclude here in a matter of a few minutes.
no, it's
Here's-
important. Yeah.
Yeah. Here's the breakout point, and the water rose up above these terraces here, and they've dated these terraces that you can see here. So the study area showing the various terraces, and Wanren Cave is located on Terrace 3, right behind the yellow dot right here. So can you see it? There's a cave right here.
Mhm.
Okay, now this is very interesting. So the cave, so one of the four terraces flanking the river that's outlet into the Shigu Basin. The third terrace up from the river level, there's a cave. Inside this cave, called the Wanren Cave, are paintings on the walls near the entrance. The paintings were dated to between 13.3 and 8.5 thousand years ago. How interesting is that? Now, that means that these cave paintings could have gone right back into the other side of the Younger Dryas if they're 13.3 thousand years old. Right?
Mhm.
This fact meant that the terrace formed prior to the period of the paintings and probably dated to the late glacial period. Trenches were dug in the floor of the cave to examine the depositional sequence of sediments. The trenches were up to about 7 feet deep, and commenting upon what they found, the authors state that the presence of cultural layers and cave paintings at Wanren Cave indicates that ancient humans inhabited the area for an extended period. However, these layers are overlain by fluvial sands and gravels situated approximately 86 meters above the modern river level. And that works out to be about 282 feet. So think about that. As a result, these fluvial sand, that's supposed to be and gravel layers, have been classified as outburst flood slackwater deposits. The lower part of the rock surface, on which the cave art was discovered in Trench 1, was buried by outburst flood sediment, and that the upper part of this surface was untouched, indicates that this level represents the maximum height of the flood water surface that came through here. Now, here's the picture. There were people living in this cave, and they had cave art on the walls. And a flood came through that was almost 300 feet deep, submerged the cave. Let's go on and see what they say, let's pause and take stock of what we have learned. When the flood came through, it submerged the floor of a cave that was 86 meters or 282 feet above the modern Jinsha River. The fact that the cave paintings should be higher still indicates that this level was still lower. The floor of the cave was still lower than the maximum. The authors estimate the discharge was about 2 million cubic feet per second. This would have been an extraordinary flood by all accounts. The floods of 2019 did not reach this depth because diversion channels successfully lowered the maximum water level. And to emphasize an important insight, quote, the presence of fluvial sediments overlaying the cave painting and cultural layer in Wanren Cave provides compelling evidence that this ancient settlement met its demise due to a catastrophic outburst flood. The authors point out that the outburst flood peak discharged is 4 times greater than the Layuan hydroelectric power station's 500-year flood, and 3 times greater than the 10,000-year flood. They also cite evidence that there occurred liquefaction of fluvial sand near the dam site in the Shigu Basin. This indicates the likelihood that the landslide that created the dam was triggered by an earthquake. One could realistically speculate that any cultural activity, such as an encampment or settlement on one of the terraces below the Wanren Cave, that is, lower than 282 feet above the modern river, would have easily been swept away in the flood, and no remnant of it would remain.
Not a chance.
Not a chance.
Yeah. Bad day.
Bad day, yeah. So now I wonder, I mean, the age date of that flood could have put it at the beginning or the end of the Younger Dryas, or it could have been younger. But it looks like, because you know that earthquake seismic shaking will cause liquefaction of the
Yes.
soil. Yeah.
Yes.
So by finding sand surfaces, sand deposits that have been liquefied led them to think that the landslide may have been triggered by an earthquake. Or could an earthquake, just think about this, if you had a subsequent landslide into the lake that created a large wave and overwash, that could be what triggered
Yeah.
the dam failure. We don't know. It could have simply been a rising water level, a heavy monsoon season caused an overtopping of the dam by a uniform rise within the lake level, or there could have been something else like a following earthquake or additional landslide, because even if you had a smaller landslide into the lake itself, because it could have been, that you had a sedimentary dam there, and the river caused the lake to rise to the dam level, and then it was just a spillover like a waterfall.
Yeah, that's what I'm thinking along those lines. Because think about it this way: if that's an area that's geologically unstable anyway, it's a mountainous area, so there's going to be faults everywhere.
Yeah.
And then you have, when you say a dam, really what you're talking about is an accumulation of landslide rubble,
Yeah.
which is not
Yeah.
going to be homogeneous. So there's
Correct.
probably water kind of flowing through it anyway. And then over time, those lacustrine sediments are fine, right? So that's going to blind off that, right? And then
Yep.
that'll continue to get the water level higher and higher and higher, with some flowing down there, right? I'm sure it had to be flowing to a certain extent.
Mhm.
And then it gets to the point. So let's say if you have now an added amount of weight from that lake over in that area that wasn't there before,
Correct.
I
Yeah.
mean, that could trigger something locally, sure, right? It could,
Hmm.
and that could start enough of a seismic event, especially if you had saturated sediments to blow that obstruction out. So I don't know. Yeah, it's interesting, but it's I'm sure they thought about some of this stuff when they built it, but maybe they just felt like they needed to build it.
Well,
And
I think what they're finding out is that, their estimates might be too low.
well, the asset, right? The dam has a lifespan
Yeah.
with
So,
probably no retirement plans of the asset, but they're probably banking on, okay, well, it's
yeah,
not gonna happen tomorrow.
we ought
So.
to get a couple of centuries out of this,
Right. Yeah. Right.
maybe.
What happens when the next landslide gushes down and then forces the water up and through the dam?
Well, that's the thing. And if you've got a row of them, then you start getting an additive effect if there is a
Yeah.
breach. So
Yeah.
Well, what did we say? How many dams were they going to build?
it was a lot.
30,
30?
20, they've built
20
7,
something,
23 more.
Yeah. Okay. Now, think about that. Now, think about the fact that they've now found evidence of 900 landslides along that reach of river. Now, what's the dating on those landslides? I have no idea. I mean, how long are these all Holocene, or did they go back into the Pleistocene? How far back do those 900?
I wouldn't imagine they can go back very far because that's an erosional kind of an area, right?
Yeah, that's what I would think. And what was the right? The glacial.
Yeah.
So could it be landslides are a lot more
I think they've been happening all along. That'd be my guess. They happen, stuff washes out, more of them happen. I know. It's interesting. But yeah, don't underestimate the power of water, right?
oil.
No doubt.
That would be a grave mistake.
That's it. Gravity and water always wins.
That's what it seems like. Yep.
Yeah, it's heavy. That's interesting.
Well, there's a lot more.
That's straight from the newsletter in the last month. So yeah,
Mhm.
we'll sign up for that and get Randall's commentaries on the latest scientific papers. Not all of them, but a couple he gets drawn to, and learn about the tours and conferences, whatever else coming up.
Yeah,
You got wrapping
I mean,
thoughts
there
on
was,
that?
you know, like the next article I've got in there is entitled "Vast Armadas of Giant Icebergs."
Which is incredibly interesting. Yeah.
Incredibly interesting.
Yeah. Yeah. Plowing
Ar-
grooves in the bottom of the ocean. Yeah.
Armadas. Yeah.
Armadas, yes. A just published study of a submerged ridge called the Jan Mayen Ridge, located in the polar North Atlantic, reveals the presence of gigantic plow marks at depths of up to and in excess of 1,000 meters or 3,280 feet. Think about that.
That's
An
crazy.
iceberg that's so big, it's creating plow marks on the bottom. There's a ridge that they floated over, and as they did, they gouged plow marks in the top of it, and those plow marks are a full kilometer deep.
Yeah. It's crazy. That's east of Iceland.
Yeah,
Yeah.
yeah.
It's,
So
But that's only 0.004
yeah, that's what.
dot.
That's exactly right. Yeah, you might get up to a little bit over 1/100% there. I don't know,
Hey.
but yeah, that's a big deal. Some of those I read it. I mean, some of those are
is that one of the papers I sent you?
yeah, and your commentary. I mean, it's they were wide too. I mean,
Oh yeah.
and the gouges are prominent. There's a history of those gouges in much shallower water. That's a long known fact, right? But from normal movement, but that to get that kind of depth and movement and stuff like that, there's a
Yeah.
lot of power behind that. Yeah,
Yeah, I mean, this was a huge discharge event of iceberg.
because they would grind to a halt, right? If they're digging in as deep as they are to make those marks, and but something was pushing them. So there's something going on. Yeah, outflow, something. Yeah.
Aha.
All right, boys.
So Chuck, yeah, you got any amazing wow fact you can leave us with here from your depths of knowledge of entertaining stories you got? Something popped to mind here about floods or a trip or yeah.
I have, and again, I've always had uh, I like well, with geology, one of the reasons I like it, I like punctuated equilibrium, right? You have
Yes,
equilibrium with
exactly.
things that happen, and so I've gone to some of these places. I've gone to I even went where the Johnstown flood was. You can to this
Oh
day you
yeah.
can see right that and the breach of the dam, which is not that big, but a lot of water came down through there. And to this day, if you know where to look, you can still see where the trees were wiped out, things like that. And you know, you wonder what makes you in life, but I've got a I've got a table out here that I don't know. It's full of these little shells are called lingula, and at one time that was a dominant life form that at least we have a fossil record of. And I have a table made out of that stuff. They're all dead. There's layers and layers of them dead. What killed them off? I don't know. So and it's
Hmm.
this the study of this stuff is I guess I don't have a story, but I got to tell you, this is all fascinating. Everything that you talk about, I mean, I like, and there's a lot more. But anybody that's interested in this stuff is
Well, I mean, you've been on a number of trips with us now and
oh
seen
yeah,
some of the spectacular landscapes that are the end product of these great fluvial catastrophes.
yeah,
Cataclysm, that's the Greek word, which means a catastrophe caused by gigantic water flows. Cataclysm. And
yeah, and it happens more often than you'd think.
that's right.
And it's not an understatement, right? That 99.999 whatever percent of anything that's ever lived on this
Oh,
earth is extinct.
yeah,
Yep.
it's gone. Yeah, well, that
So catastrophe is the norm of the planet.
yeah, one of the mass
extinction.
extinctions. Yeah, one of the mass extinctions wiped out 90% of life.
Yeah.
That's
Yeah.
kind of figured that way,
That
right?
was the Permian Triassic connected with the Siberian traps.
Yeah,
Mhm.
90%.
And
I mean,
I do talk about in Squaring the Circle on the multi-episode part of the Tunguska event. I think I've got 3 episodes devoted to the Tunguska. I talk about this correlation between the impact, the geography of the impact event, where it occurred, and this coincidence that it was targeted directly on the core of this paleovolcanic outburst point.
Yeah.
So check that out. I think that's in the third episode about Tunguska, if people are listening to this.
Okay,
And-
good. Yeah, I wanted to ask you if you wanted to say anything about Squaring the Circle that's over on Rumble. Hopefully you're talking about Cosmographia when you're doing that
Oh, yeah.
show. But yeah, Squaring the Circle has got, what, 15, 16 episodes over there now? So
We're
check
number
out Randall.
16, I think.
Yeah, excellent.
So Bradley, I'd like to get you on there as a special guest at some point soon.
Well, that sounds mighty special.
Well,
We should do
yes.
such a thing.
Yeah, but
All right, cool.
I wanted to thanks for the invite. I really had a lot of fun.
Yeah, and we're gonna have
Chuck.
I really look forward to getting back out on the road with you, Chuck. We had
Me
we had
too.
a really good time.
Yeah.
Yeah,
Yeah,
if you're gonna have some more
absolutely.
time coming on, that's exciting. We'll do some fun stuff, and you guys are semi neighbors down there in North Georgia, and
Not far away.
I passed
Well, maybe
right by, so
maybe
we'll
Chuck, we
connect
could do
again soon.
something local. I mean, there's still all kinds of places I want to explore up in Western North Carolina, Eastern Tennessee,
Sounds good to me.
Cumberland Plateau, all of that.
No doubt.
Yeah, good.
All right.
It's a plan.
Thank you.
And think about this, we could go up there, when we did one of our trips to where we went through the Smokies and that area up in there, it was summer. So there was a lot of stuff that you could tell
Couldn't
was
see it.
worth seeing, but would be a lot easier in the winter.
I'm with you on that too. Yeah, Mid Cumberland tour, those kind of tours. Yeah, it's easier to see it in the winter.
Yeah.
That's why people say the geology out west is so fantastic. Well, there's no
Right.
trees on it. It's the same here.
It's naked.
But yeah, so we just need to get rid of all these trees.
Oh, let me think about that. I'll get back to you with an idea.
Okay.
All right, gentlemen, good stuff. Great job.
Yeah, good stuff. Really enjoyed it seeing you, Chuck, as always.
Likewise.
Your jolly face.
Likewise.
All right.
Your warped and weird sense of humor.
Yeah.
We all need more jelly. Leave that as the theme.
Well, you got to laugh sometimes, right?
All right. Safe travels, brother. Yeah, we'll catch
Yeah,
up soon.
thank you. Yeah,
Okay.
I'll get to bed and I got to get up 3.5 hours. So.
Yeah, crazy.
Oh my God, get
All
out
right.
of here. Go tuck yourself in, Chuck.
Yeah, it
Good
won't take
episode,
long to do
Randall.
it.
Always lots more. We'll be back on Cosmographia. All right, good night.
Take care. Good
Good
night.
night, Chuck.
Good night.